Welcome back to The Explainer. If you loved our previous deep dives into Retrieval-Augmented Generation, RAG, you're absolutely going to love this. Today, we're exploring the absolute cutting edge of information retrieval, GraphRAG and hybrid search. We're going to figure out exactly how developers are building fundamentally better, just way more accurate AI brains.
Here's our roadmap for today. First, we'll hit the limits of vector search, then the power of hybrid search. Third, we'll enter the knowledge graph. Fourth, we'll look at hybrid RAG as the ultimate combo. And finally, evaluate the new RAG.
All right, Section 1, the limits of vector search.
Okay, let's dive into this. The core problem we're tackling today is that pure vector search, as incredible as it is, simply isn't enough for enterprise-grade AI anymore. Think back to the standard RAG baseline we're all familiar with. We take big documents, chunk them up, run them through an embedding model, and store them. Then, when a user asks a question, we embed that query, do a similarity search to find mathematical matches, and feed that context straight to an LLM. It's brilliant for understanding broad semantic meaning at scale, but it has a pretty glaring blind spot.
Picture this. A user types a highly specific query into the system, something like error code 0x80070005. With pure vector search, the AI tries to find conceptually related content. So maybe it surfaces some generally helpful articles about, say, Windows permissions errors, but it completely misses the one document containing that exact hexadecimal string. Standard RAG just fails miserably here because it misses exact keyword matches. It returns conceptually related, but literally useless documents for the specific task you actually need help with.
Which brings us to Section 2, the power of hybrid search.
And this brilliantly illustrates the immediate, elegant solution for that exact match failure. It's all about taking two parallel paths. On one side, we have dense retrieval, that's our standard vector search, which is great at capturing broad semantic meaning and complex intent. On the other side, we have sparse retrieval. This relies on algorithms like BM25 for exact keyword matching. See, pure keyword search misses the concept of scaling web applications when you search for horizontal scaling. But pure semantic search misses our specific error code. Hybrid search simply says, hey, why not both?
So how do they actually combine under the hood? Well, the system runs both the sparse and dense retrieval simultaneously. Both of those paths return their top candidates. Then, a fusion algorithm merges them into a single ranked list. The industry standard for this is called reciprocal rank fusion, or RRF. By looking at the ranks of the documents rather than just their raw scores, RRF smoothly and robustly merges BM25's unbounded relevance scores with the neat 0 to 1 range you get from vector similarity.
And the tangible, real-world impact of doing this is massive. According to Microsoft's benchmark testing on production customer indexes, hybrid search achieves an average relevance score of 48.4. That's a measurable, definitive accuracy improvement over the 40.6 you get from keyword-only or the 43.8 from vector-only approaches. What that means for us is higher precision, way fewer irrelevant documents eating up your context window, and ultimately much lower LLM API costs.
Moving right along to Section 3, enter the knowledge graph.
Now, while hybrid search absolutely fixes our keyword misses, what happens when we need complex reasoning across dense, jargon-heavy documents? Think about stuff like financial earnings reports. We have to completely rethink how we store data, moving way beyond just simple text chunks. Enter the knowledge graph triplet. Now, I know that sounds a little intimidating, but it's really just like basic grammar. A triplet is the fundamental unit of information in a knowledge graph. It just consists of a subject, a predicate, and an object. It represents data as an interconnected web of relationships.
Let's look at a real-world example to make this concrete. From an incredibly complex, totally unstructured financial earnings report, we can use an LLM to extract a clean, structured triplet. Something simple, like company X acquired company Y. This is exactly how complex text is transformed. It allows the AI to traverse literal relationships rather than just kind of guessing at semantic similarities in a vacuum. It drastically improves information extraction when you really have to follow a trail of logic through complex formats.
Which leads us to Section 4, hybrid RAG, the ultimate combo.
This is where engineers are fusing all these concepts into a single powerhouse architecture. When you ingest a complex document, hybrid RAG processes it in two distinct ways at the exact same time. On the left side here, we have the standard vector chunking we covered earlier, creating dense embeddings for semantic search. On the right, that exact same text is pushed through a language model using specific prompts to extract those structured knowledge graph triplets.
So your system now possesses both a broad semantic understanding and a highly structured relationship map of the exact same data.
Let's move to query time and see how this builds. First, the system retrieves the most similar vector chunks. Second, it retrieves a relationship-rich subgraph from the knowledge graph, and this is usually constrained to 1 degree of separation from whatever entity you queried. Third, it concatenates both of these contexts together. The vector RAG context gets appended first, followed right after by the graph RAG context. Finally, this massive, unified context is fed straight into the LLM to generate the final answer.
Now you might be wondering, doesn't maintaining multiple indexes create a huge bottleneck? Well, the infrastructure has totally evolved to handle it. For instance, Redis can sustain 66,000 vector insertions per second. That kind of extreme throughput is absolutely vital to combat the cold start problem in hybrid systems. It allows developers to backfill massive amounts of vector or graph coverage across huge corpuses basically instantly, without compromising query latency at all.
Finally, Section 5, Evaluating the new RAG.
We've seen the architecture, but let's look at the actual data to prove mathematically why this advanced setup is fundamentally better. So, the crucial point is this. When BlackRock evaluated this on actual financial transcripts, they discovered a really fascinating dynamic. GraphRAG dominates on extractive questions. Those where entities are clearly defined. But vector RAG actually performs better on abstractive questions, where the information isn't explicitly spelled out. But hybrid RAG, it provides the ultimate performance balance. It outperforms both individual methods in faithfulness and answer relevancy. It essentially acts as a safety net. If vector search misses the context, the graph picks it up, and vice versa.
To ground this theoretical architecture in reality, we can look at the recent White House executive order on promoting advanced AI innovation and security. This directive outlines a huge push to secure civilian federal government information systems and protect critical infrastructure against criminal actors. It heavily emphasizes the need to adopt advanced AI-enabled defensive tools and even facilitates access to what they call covered frontier models for operators of critical infrastructure, places like rural hospitals and utilities.
And that perfectly encapsulates why mastering this hybrid architecture matters so much right now. We are moving rapidly, like incredibly fast, from simple Q&A chatbots to highly capable autonomous systems. With hybrid RAG, we're deploying AI that can pull exact database metrics using sparse search, trace intricate corporate acquisitions through knowledge graphs, and reason across vast enterprise datasets all at once, which leaves us with a critical, provocative question to end on. Are our cyber defenses ready for agents that can think, search, and reason entirely on their own? It's something you absolutely must consider as you build the next generation of AI.